session, we're on about Ceph now, and Orit has come from Israel to tell us about object storage.
Hello. Can you hear me in the end? I know I have a low voice. No? Yes? No? Yes? Okay. Hello, I'm Orit Wasserman. I'm a Ceph developer in Red Hat Ceph team. I've been working on storage quite a while. I started working on distributed block storage in some Israeli startup. Later I moved to work on distributed file system in a startup called Exonet that was later acquired by Dell, became its Fluid FS product. And sadly, last year, due to the merger with EMC, they closed it down. I did a break, worked on KVM hypervisor, nested virtualization, and migration. And in the last 3 years, I'm back in the storage world, and I'm working on software-defined object storage. And today, we're going to talk about object storage. What is object storage? Why should you use it? And when you shouldn't, actually. And how Ceph implements its object storage. So what kind of storage do you know exists, except object storage? No one? No storage? Block storage, correct. What and file system. Those are the main ones. So let's talk about them in general. And it doesn't work. Okay. So we're talking about block storage. You just write your data. You don't have metadata. You pick a device, pick an offset, and write the data. You, the user, the application, manage everything. You need to know what you wrote where, what exactly was the data. It's really fast as it's really more or less layers, but it's much complicated for application to use block storage. Usually people use block storage when they need the latency and performance. For example, big databases will benefit from block storage. But we, as users and application, that's not enough, so we use file system. And file system has much more. First of all, a way to organize the data. We have directories that can contain other directories and files, and that way we know sometimes you forget where you put your file, but we can know this directory is my source, and the source is divided into directories. It's very useful us as user. We have metadata, we have ownership, we have access control and permissions, authentication, we can even share files, and we don't need to think how to place it. We have in-place write. I can create a file of 1 giga and write inside it for just 4Ks. And the file system will support it. So everything is great. So why do we need another kind of storage? What happened in the world is that storage grew and grew, which is really good for us storage developer, but it got really, really big, and you wanted it to scale, and you needed to in cloud, and file system seems to not a good fit in that case. So let's look at the file system and think what parts of the file system make it more harder to distribute and scale. Anyone has any idea? Sorry, again? What do you mean metadata? Yeah, it's true. It's maintaining metadata, but it's actually not the ownership and permission. Metadata is more complex. So first of all, I talked about the hierarchy. So any one word file system can know hierarchy can be really, really deep. Like I've seen someone with actually like 1 million files. I don't know how we maintain it, but the deepness was huge. So that's one thing. And for me, at least, even if I use file system, actually, now I don't remember where I put my files. I usually search if it's something I didn't use for a while. I search it, and then I find the file. So the one thing is the hierarchy, and we talked about metadata. So who here knows what inode is? Great. So what do we store in the inode? First of all, yeah, the metadata, ownership, permission, but we store something else in many cases. Yes?
Yeah, the starting sector.
Again?
The starting sector of where the data is actually.
Exactly. Correct. It's not exactly the study sector. It could be part of. But when we write to a file, we need to allocate the space in the block device. And we actually write in several different times. So we'll have lots of those allocations. And we need to store this mapping, where the file is on the block device. So we said we have a problem with hierarchy. How will we solve that problem? Hierarchy is complex. It could be really deep. What can we do to solve it? And the answer is very simple. No hierarchy. Well, not really. You need some hierarchy, flat namespace. We have a bucket or container. It contains the object, but it cannot contain other buckets. One level. Very simple. And it's enough in most cases. We talk about the file mapping. Where is the file in the block device? How will we solve that? We want static mapping. What does that mean? We always write the whole object. There's no partial writes or in-place writes. That means we can do the mapping really static. When you say immutable object, it doesn't mean you cannot change the object, but it means you change the whole object. If the object is 16 mega, and you write another 16 mega, it will write new 16 mega. You cannot do any in-place writes. This simplifies the mapping. So object storage is a flat namespace. S3 uses buckets, we use containers, but NSF uses pools, for example. But you have this bucket of objects, and the object, you have ownerships, you have access control lists, you have user metadata, which is quite unique because in file system, the metadata is the file system metadata. But in object storage, we allow users to create their own metadata, and that helps them. We talked about one level of namespace. So in that case, you can use the metadata to find your objects. You don't need a complex path. We have integration, and objects are immutable. So everything was great. And in 2001, there was a paper on object storage. There was a standard OSDI. It's object storage on SCSI. And EMC had a product, Centera. But so object storage was in the research. I was in research that only research uses object storage in very small cases, specific cases. So what changed and make object storage popular? In 2006, an online bookstore decided actually it's a cloud provider and published the first cloud, Amazon. And Amazon had their cloud, the EC2, but they also had storage. S3, which means simple storage service, and S3 is object storage. But they changed one thing. What API will you use for storage in a cloud environment with internet base? HTTP, REST API. They took the idea of object storage and put on it REST API. That's Amazon S3. And people liked it. And we have every cloud provider has its own version. They are similar, but never quite the same, because that's life. Most people use S3. That's the most common one, and most applications do integration with that. We have OpenStack Swift. Google has its own Google Cloud Storage, and Azure has its blob storage. For some reason, okay. So what kind of API we have? We can create the delete bucket. We can list all the objects in the bucket. We can change access control per bucket. We can put object, which means we write an object. We can read it. We can read it, and we can actually read a range from an object. You don't have to read the whole object. You can read part of the object. You cannot write part of the object, but read you can. You delete it and change access control on objects. This is an example of how HTTP request looks. As you see, it's not really simple. You have the HTTP commands, put, get, delete, post, head. And you have the URL, which actually is important. You have parameters in the URL. And you also have very specific headers in the HTTP, which Some are Amazon specific. There's no example of Swift here, but Swift has its own headers. And it's quite complex. Luckily for all of you, when you use object storage, you don't need to do that. I'm a developer, so I do curl requests like that. Usually you have very nice SDKs. You have a Python SDK, JavaScript SDK, Java, Go, Perl, Python, everything. And you use that to access cloud object storage. First example, this is Flickr. I like Flickr. It's yellow because they use Ceph. And they use the Ceph to store your photos. So if you think about what is an album, how do you map it to object storage? We have several albums. An album is a bucket. So I could do an album of Bernard, an album of some other trip I do, and each will be a bucket. And each photo is an object. And even if I decide I need to rotate the object or maybe do some change it a bit, it's coloring, I still, when I write, I need to write the whole photo. I cannot put part of it. So it's really a classical way to store for object storage. Has anyone ever, well, it's actually here probably will happen. You try to upload a photo, and it said, okay, it's going to take half an hour. You went to take your coffee, went back, and you got an error, a network error. And you say, oh, again, I need to upload the whole photo again. For that, we have a different way to upload and download big objects. It's called multipart, and it's the same. The name means we take a big object and we divide it into parts, and we upload or download each part separately. The benefit, one, in case we have an error, we only need to upload the parts that didn't get uploaded, not everything. And we're talking, and actually object can be really big, so if you want to upload 1 giga and you already upload half a giga, then you only have half a giga to upload. Also, we can use parallelism and upload parts in parallel. We can get better bandwidth. Multipart protocol is transaction-based. It means that you initiate the upload, you start uploading the file, and only when you're done, you do complete, and only then the actual object will be created on the storage. You can use it to upload an object you don't know the size. Let's say you stream from a video camera, and you want to upload the recording only to be created only when you complete. You can still upload parts of the streaming all the time, and then you complete it, and then you have your recording. So it's very efficient. And you also can use multipart upload as transaction. If with file system, usually when you try to do a transaction, you either create a temporary file and then only in the end rename it. Here you can do the multipart upload, and only when you complete, finish the transaction, you'll get your object. And we'll usually have a parameter. We mean how long can we keep ongoing multipart uploads, because some cases would never complete. And the object storage will automatically delete the ongoing multipart that are too old. Usually it's a few hours. Another example of object storage is to store documents. So here's my Google Drive. And I can not only upload my presentation, but I can also have versions. Every time I upload a new version, I can keep the old one. And then if I need to roll back on one CD files, I have all those. And another cool feature is that you can see on top, the Google Drive keeps versions up to 30 days. So it means the object storage will delete automatically all the objects within 1 month. Those are very two important features in object storage that don't exist in a file system. So first one is versioning. Actually, there was one file system that had versioning. Who knows what file system had versioning? I think it does. VMS file system had versioning, which means every time you write on a file, you get .1, .2, .3. So, but since then, I've never seen versioning. So the idea is that you can set versioning on a bucket, and from that moment, every time you overwrite an object, it won't overwrite the original object, but create a new copy, not a new copy, a new instance. And you can, when you just read an object without saying which version, it will give you the latest version. But you can read an old version by specifying, giving it the version ID. You can list all the object version, and you can delete a specific version. But there's one problem in versioning. Anyone can guess what's the problem in versioning? Space, exactly. It takes space. Every time I write one, let's say I want to write 1 giga, every time I write 1 giga, I'll have another 1 giga. So for that, we have life cycle. And the most common life cycle is rules, automatic rules to change object transitions. The most common one is expiration. I can set a rule when I want an object deleted. It could be that it's too old. For example, it's more than 1 month, and I want it to be deleted, and the object storage will delete it automatically. You can do more complex rules, for example, number of versions and very complex stuff. And the other uses is steering, moving in between cold and hot storage. Object storage always have access control lists per object and per bucket, but there are cases we need more fine granularity. For that, we have bucket policy. It's a way to share buckets between different users. When you have your own bucket, usually you can be the only one accessing it. You can make it public, but that means everyone can access it. And that's actually, in many cases, all the like you can see, I think last week where there was someone on AWS H3 that allowed did some information public. And when you do public, it means everyone on AWS can see it. You don't want it. You want share between users, but only between those users. So we have bucket policy. It allows sharing, and it also allows limiting the access. For example, the most common one is allowing access from a bucket for a specific IP address or a list of specific IP address. This way you control all the access to your data. We talk about the fact the user can add its own metadata. The most common example, I talked about photos. So we can tag and add tags to photos. I can say this photo is a photo of my daughter, Tamar. So then when I look for the photos of Tamar, I can see only those objects, those photos that have the tag name equal Tamar. It could be location. Those are in S3 called tags, and we can search for objects with specific tags, and we also can do the life cycle, for example, expiration, according to the tag. So I can say, never delete any photos of my daughter, forever. I'm willing to spend the space. And object storage has lots of very, very cool features. We have hosting static websites. We have usage logging. It's very important for cloud because we want to bill our customers. We want encryption because it's very important, security of your and privacy of your data, and we have compression so we can save space. And it's compression per object. We compress each object. Next, we're going to talk about Ceph and how Ceph uses its object storage. But before I can talk about Ceph object storage, I want to talk a bit what Ceph is. So who here heard about Ceph? Cool. Well, not cool. I'd say everyone. Who here uses Ceph? Oh. Who here uses Ceph object storage? Only RBD. What do you use? Yeah, cool.
And production.
Production. Oh, cooler. Okay. So let's start with the name. So Ceph is a short of cephalopod. It's marine animals without bones. Octopuses and squids and all those. And its version, we move alphabetically and choose one of those. It's very important. Every version, we have a very big discussion what should be the next name. The current release, stable release, is Luminous. It's a squid that you can see in the dark. And the previous one, which sadly was short term, is Kraken. We really liked it. The next long term, we don't no longer have short terms, only long terms, is Mimic. So what is Ceph? First of all, it's an open source project. We are part of Red Hat. Everything is open. You can see all the code in GitHub. We also have an IRC challenge, like every open source project, and mailing list. It's a software-defined storage. Who here heard about software-defined storage? Really? This is a buzzword. Okay. So software-defined storage is like the next step of distributed storage. One problem you usually have with distributed storage is that you need many cases, you need very specific hardware. Sometimes even the companies, let's say Isilon, its node is manufactured by Isilon. So even if you want to expand the storage, you need to buy very limited hardware. But that's not what happens. Usually you want to use commodity hardware. You just want to buy in the next available server, add disk, and extend your storage. So software-defined storage is much more flexible, and it can run on many different kinds of hardware, many different configurations, and that way you can scale it easily. You can use old hardware or new hardware together, and it's much easier to deploy in really, really large scale. Ceph has unified storage APIs. You can use Ceph with block device, RBD. You can use it with its file system, CephFS, POSIX-compliant file system, and with object storage interface we call Redis Gateway. It's distributed and massively scaled. When you talk a large scale, that's the idea of Ceph. Our minimal number of nodes is 5. We don't recommend less than that, and that actually the small number. Ceph is always better in large scale. It has no single point of failure because that's how you do distributed system. Because we talked about large scale, we cannot keep one copy of the data because then we for sure statistically going to lose it. So Ceph has a built-in replication. At default, it's 3 copies. 2 are not enough in most scale. And we also have eraser coding to save space. Up till Luminous, you could use eraser coding only with the object storage, but from Luminous, you can also use it with RBD and CephFS. We talked again about massively scale. We talked about sometimes 10,000 of disks. We have to have self-healing. Ceph actually detects there's a problem and recover it automatically. For example, if there's a failure in some disk, Ceph will detect it, and all the data that was on this disk, let's say a huge replication, will be replicated again. So let's still have 3 copies. Ceph has, as I said, a CephFS with a POSIX-compliant file system, RBD for block storage, especially for virtual machine images, and Redis Gateway. All of those use a layer called Redis, which is actually what we call a Ceph cluster, Redis. And I'm going to explain what Redis is. So Redis is reliable, autonomic, distributed object storage. So underneath it all, Ceph is object storage, but it's not cloud object storage. It doesn't use REST API, and it's a bit different than the regular object storage. It's a strongly consistent system, unlike, let's say, Amazon S3, which is eventually consistent. It provides us the replication and eraser coding. It's a flat namespace with pool. We don't call it bucket, we call it a pool, and objects. It has very complex placement system. We use a system called Crash. Crash is hash-based, so we don't have a single name service to find the placement. And you can also configure Crash to be topology aware and hardware aware. And this way, for example, you can have a pool of, you can set, for example, you can define what a rack is. So if you want your fellow domain to be, like if you lose one rack, you still have your data, you can set up Crash so it be aware what rack is. In that case, if you lose, let's say, connectivity one of your rack, we can actually still provide you with data in that case. And for better performance, we serve direct line to server data path. We have two kinds of node in a Redis cluster. The OSD, the Object Storage Daemon, is a smart storage node. We have 10 to 10,000 OSD in the cluster. I think the biggest one today is at CERN, and they have, I think, around 60,000 OSDs, maybe more. Well, Greg knows, but he's not here. It's a 1 OSD per disk, or RAID group, but we prefer you use disk without RAID. We don't need, we do the application as a code ourselves. It stores the object to the client. Client, when they need to read an object or write an object, connect directly to OSD. And the OSDs are responsible also for recovery and replication, and they use peering in order to see the other peer status. And they can actually detect a failure and alter the recovery automatically. The other kind of node we have is monitor nodes. Those we have a small odd number in a cluster. They maintain the cluster membership. And as we're talking about cluster membership, we need a quorum, so it should be odd number. Usually the default is 3 monitors, but really, really large cluster like CERN need 5. They don't serve any object to the client. They just handle the membership and cluster membership changes. So this is an example of a Redis cluster. We have the 3 monitors and many OSDs. And the client, when they connect to the cluster, then get the cluster map from the one of the monitors. And then they connect to the OSDs directly without going through the monitors, unless there's a failure somewhere. All the services access Redis by using libRedis API. It's a very rich API. It's much more than object storage API. And next talk, Greg's going to talk more about libRedis. But I'll talk about a few features we use for the cloud storage. So the most important one is the efficient key value store in one object. We call it OMAP. And we use it for a bucket index. Single object compound atomic operation. You can actually, for atomacy in a distributed system, you want to sometimes do several operations on an object, and Redis allows that. We have Redis classes. Classes is like store procedures on MySQL. It means we can actually write code that will be run directly on the OSD when the object changes. This way we don't need lock-in, and we can save very complex distributed algorithm. And we have what's notify on an object. We mean we can register on an object, and when there's a change in the object, we'll get a notification. We, for example, use it for our metadata cache. So let's talk about cloud object storage. So first of all, Redis Gateway is the cloud object storage gateway, which means he has to have REST API support. We mean it has to give HTTP interface. So we have an HTTP server inside of Redis Gateway. Currently, we're using Civit Web, which is an open source C HTTP server. We support S3 and Swift API. They are mostly compatible. In many cases, you can use them both, but there are corner cases when you cannot use both on the same object. And Redis Gateway uses libRedis in order to communicate it with Redis cluster. Redis Gateway is stateless. All the state is stored inside objects in Redis cluster. That means it can scale up. If you need more performance, you can run another Redis Gateway on the same Redis cluster and get better performance. But we don't just need the REST API. So let's compare for Redis Gateway object and Redis object. So Redis objects are limited in size. The default is 4 mega. You can increase it to 8 or 16, but that's the size. Who knows how maximum size of an object you can create in S3 with multi-part output? 5 tera. So you can create an object of 5 tera. So that means that's not enough for us. Redis has mutable objects, which we don't need because cloud object storage are immutable. One issue is that the pools in Redis are not indexed, which means when we list the object, we don't get them sorted by name. But in cloud object storage, you need the list of the objects sorted by name. And the ACLs are per pool, but we need SELs per object. So in Redis Gateway, we need to extend Redis to support all these operations. And of course, all the special cloud object storage features like versioning, multi-parallel upload, and so on, lifecycle. So how we create our object? So we take one S3, let's take an S3 with the same. We take one user S3 object and create several Redis objects from it. So every object has a head object. It contains its metadata, and we have room for small objects to actually write the data in, up to 0.5 mega. And then you have tail objects, depending on the object size, from 0 to the object data stripe to 4 megabytes. If you look how we do the mapping, I talked about the mapping. So the head is always the bucket ID and the object name, and the tail are the bucket ID and some UUID. That's to allow us versioning, and the UUID is kept in the head. And then it's just, depending on the object size, the number of tails. So it's very simple mapping. You actually just need the UUID and the object size, and we can know how much exactly parts we have and where each part is. We talked about the bucket index, so we need a sorted list of objects in a bucket. For this, we use the OMAP. It allows us to do list keys and list values sorted. And the bucket index just has the object name and some attributes for each object. What happened was that in our object storage, users don't like buckets. I don't know. Usually users have very small number of buckets, and they store almost all the objects in the bucket. So Yahoo used Flickr. They found out that, users don't have too many objects in one bucket. So for that, we have Yahoo added sharding, which means we take the bucket index and we use several OMAP objects. We shard it, like you do in database. And that way, we can scale the bucket index because you cannot store, millions of objects in one bucket index. So we get too big. You'll have lots of latency when you create an object or delete it. And also, it will get too big for one Redis object. So Yahoo added the sharding. From Joule, we found out that users don't think ahead, and when they create bucket, the sharding was static. When you create a bucket, you would set the number of shards. What we notice is the user don't think ahead and just create a bucket with the default shard number, which is stored unrelated to the actual number of objects they're going to store. For example, they can get to 10 million, and actually I've seen 500 million in one bucket. So we added the option to offline reshard in a bucket, so you can change the number of shards, but offline. From Luminous, we have online resharding, and also we added dynamic resharding, which means Redis Gateway actually detects when the bucket index is too big, and we shard it automatically for the user, so they don't need to think about the number of shards they need. We have several metadata that are needed. So every time we have a request in a cloud object storage, we have to authenticate the user. Every request, this is HTTP, we have to authenticate. So first thing we have to cache is the user info. Depending on the protocol, Swift uses user password. S3 actually uses the key and secret and sign and the signature. So we cache the user info in all the Redis gateway. But we have several Redis gateways in the cluster. We need to sync the cache between them. Here we use the watch notify Redis providers. And when every Redis gateway registers on the user information, and when the user decides to change his key or secret or priority or stuff, we'll get a notification and we can invalidate the cache without any distribution blocking. We also keep other information about buckets and bucket instance, but we'll skip it. So very, very important feature in cloud is the fact that users have more than one cluster. And usually those clusters will be really far geographically between one another. The most common use case is disaster recovery. So in case there's a really serious problem in one cluster, the other one won't be affected. The other use cases they want is actually providing more closer geographically place for the user to access these objects. For that, we have Geo application. We call it inside the Redis Gateway multi-site or sync. It's asynchronous replication, almost. We have the user information is synchronous replicated because, first of all, those actions happen rarely, and they have a cross-wise system effect. And we need a way that, because if you think about it, if, for example, a user changes password in one site, you would want for sure that the other side will change that password because you cannot access the data anymore with the old password. It's very important. So that's synchronous, and also bucket meta data operation are also synchronous. The Geo application multi-site was available. The new one is available from Joule, but there was some implementation in Hammer, but it didn't work really well. So from Joule, we have Geo application in Redis Gateway. You can do, if you want, active replication. That means the data can be written in both sides. And if you want to, you can do only with standby replication. But that's waste space, and there's no reason not to use the other cluster. Also from Luminous, you can set per bucket synchronization. In Joule, it's like you create a zone, and the zone is replicated completely. From Luminous, you can actually say on the bucket if you want it to be replicated or not. Another new feature we added in Luminous is the metadata search. I said we can add for objects cool metadata user-owned, or maybe also the regular metadata. And we're talking a large number of those objects, so we need a way to search them. We did integration with Elasticsearch, so we export all our metadata to Elasticsearch cluster, and then the user can search for metadata. For example, I can add object can have a color, I don't know why, red, and I can search all the objects where the color is red. That's available from Luminous. So everything is cool, object storage is cool, but then you'll always have legacy. And there will always be, and I know Mocktail virtualization, it lives on legacy, an application that used to NFS, and your whole system moved to cloud to S3, but that application, you cannot change it. And the other use case we need for NFS is when you have an NFS system, you want to move to a cloud environment, but it takes time, and you want a way to easily export your data into the cloud object storage. For that, we provide NFS on Redis Gateway. But I have to insist, this is not a NFS gateway. If you need a file system, you should use a file system storage. It is much slower than regular NFS on file systems. And it supports most features, but not everything. We use NFS Ganesha. Anyone here heard about NFS Ganesha? So NFS Ganesha is a very cool open source project that implements NFS server in user space. I highly recommend it. And we use NFS Ganesha in order to implement the NFS protocol. And the backend is librgw, that is a library that maps between the NFS semantics, file semantics, into our object storage semantics. So what are plans to mimic our next versions? First of all, we'll have Cloud Sync. This allows us to actually sync the object into Amazon, or if you want a different public, well, Amazon S3. Other S3 supported cloud provider. And this way, user can actually have the production on Redis Gateway and back up into AWS or for disaster recovery for AWS. I talked about the fact we use Civit Web as an HTTP server. Sadly, that Civit Web is not scaling well. It has its thread per connection model, which really, really doesn't scale. And we want to move to a more asynchronous model. We're going to move to Beast, which is a new Boost HTTP server implemented library for C++, and it's also asynchronous. And hopefully, Mimic will move to Beast, and then we can scale much more. And we are planning to add STS. STS is Secure Token Service, Amazon has. Someone called it, I think it's really good, AWS Kerberos service, and user need it inside the cluster. So I hope you learn a bit about object storage today, and you see that it's really good, especially for large scale, large objects. It can be okay with small, but large is really good. It has very unique features you don't have anywhere else that really suit clouds workloads. You can use, Ceph implements really nice cloud object storage. The scale, we still have problem, but scale really high. And it's open source. And you can also use it for your file system and block. And we really like more people to be engaged in the project. We like contribution from documentation and bug reports and testing to actual code. Next, Greg will going to talk a bit more about LibRedis internals and API. This is my email if you have any questions. So, questions?
You say that NFS is so much slower. How slow are we talking?
I actually don't know the numbers. We didn't do, but it's slower because it's like you take NFS and then you move it. For example, you do in-place write. For in-place write, for example, it will be really bad because instead of writing, let's say write 4K, so instead of writing the 4K, it will write all your file. So you can see how slow it can get. Also, the mapping, NFS protocol is not really a very high-performance protocol, but the mapping between him to REST API is, again, two times. You pay for the NFS RPC and then for the HTTP. So it's double. I don't know. I don't have numbers. Usually people used to do async with it and stuff like that, which are not really performance intensive. Yes?
How's that getting to the 5 terabyte number limit? Because it's not like power of 2 or something.
Why do the max object is 5 terabytes? It's actually not Ceph. It's Amazon number. That's the limit that Amazon says. And actually, you can set it to much higher, and we support it. It's configurable. But I actually never saw a 5 terabyte object. It just takes so long to upload it. So. But I saw 1 tera. Yeah, I did saw 1 tera. Any other questions? So thank you.
So could you place a copy of the presentation in here?
What format do you want? So this is that one. No, this should be. Okay, that's one. So ODP or PDF? I think PDF.
PDF, yeah, that's fine. Okay, thank you.
There you go.
Sorry. We're planning. Amazing
That is not 16 by 9.
Well, are you aware of any like artists?
What? Is that the... I don't think the aspect ratio that this system is giving me is what that's got.
Yeah, it's not the same.
There we go, okay.
So there's
There we go, that looks better.
Yes, okay.
I can manually override it to get it to be 4 to 3.
The name of
Yeah.
the backup system, open source backup system.
Yeah.
There's the one open source backup.
So yeah, this is the microphone.
This is
so
the
you
microphone.
need to speak where
Into
that
this.
can pick up. Yeah.
Okay.
And if there are questions,
Gotta repeat
unless
it, yes.
unless they have a very very loud voice, you know, you
Yeah.
need to think, did that pick up the question?
Yes.
And if not,
Yep.
you know,
Okay.
repeat it. So
Cool. Can do.
yeah.
Yes.
Yeah. So yeah, you saw sometimes this had to change from HDMI versus VGA. You have to press on here.
I'll press on there. Well, he's set up, so.
Yeah, he's set up, but it's on here.
Okay.
So that's HDMI. So if we use the HDMI lead, you have to press that one. Yeah, to switch over. And then you remind them about the
All right.
repeating questions.
Any questions?
Yeah. And do you need a 10-minute?
10 minutes.
Well, since I'm doing an 18-minute talk, probably the 10-minute won't do anything but scare me. Yep, it's going to be very exciting. Oh, we're getting pictures. Hello, world. I should have cut a more time.